This video will focus on how we can solve the problems in this Exp.7 warm-up. First question is a money problems question, where it's asking you which is better account to invest $1,000 if you want to remove your money after 6 years. So part A says an account that will earn simple interest for 4.3% for 6 years. Part B is an account that earns an APR of 3.7% compounded quarterly. So what we have to do is figure out after 6 years which one of these two accounts has more money in it. Both of them are investing $1,000. So key thing for part A is that it's simple interest, and part B it is compounded quarterly. So first step would figure out what is that interest that you're getting every single year. So you take that 4.3%, you turn it into a decimal, so you're going to multiply 0.043 multiplied by that $1,000. Which that isn't all that difficult to do. That's going to be a total of $43. So what that means is that you get 43% or 4.3% of $1,000, which is $43. You get that for all 6 years. So your equation will be your $1,000 that you started with plus the $43 of interest that you multiply for 6 years. So this is your principal, this is your interest per year, and this is how many years that you earn that interest. Which tells us after those 6 years we get a grand total of $258 earned in interest. So we will have $1,258 if we earn simple interest in an account, right? It's simple interest because you earn the same amount of dollars given to you, or the interest, every single year. Now for compounded quarterly, that means you're going to take this 3.7% and you're going to chop it up into 4 parts because that's quarterly. So as you start out with this equation, you have your initial investment, and now we're going to multiply by 1 plus, and then your rate as a decimal, so 1 plus 0.037, all divided by 4, and that's going to be to the 4 times 6. Again, that was our principal here for 1,000. 1 plus, because we're increasing, 0.037, that's the percent as a decimal. Chop up into 4 parts because it's compounded quarterly, and this exponent 4 times 6 is the total number of compounds, which gives us here a grand total of $1,247.29, which looks like it's 0.297, which would round up to 0.30. So $1,247.30. As we take a look at the comparison between these two, we have a little bit more money in the simple interest. The rate is a little bit higher for this short time period, and so it seems to me that the simple interest is better after 6 years. Now the second question asks you to determine if this simple interest account that we've said is going to be true for part 1 is always going to be better in comparison. So what we need to do here, we need to take a look at the differences between them over time. And so we know that we earn $43 every year in simple interest, but if it says always, that would imply, well, what if we leave it in there for longer than 6 years? So you're going to have $1,000 plus $43 per year times X years, and that would be your equation for simple interest. And another equation would be your $1,000 times your 1 plus 0.037 divided by 4, your compound interest. Now 4 is a constant for us because it's compounded quarterly, but we don't know the number of years, so this equation would be 4x in the exponent. So what we would do is I would go into y1 in your graphing calculator and enter your simple interest, and y2 in your graphing calculator and enter your compound interest. And what we'll be looking for is how did those values change over time. We have a pretty good idea that it's likely the compound interest will overtake the simple interest. It's just a matter of when. So as you can see in my graphing calculator, I have the simple interest in y1 and the compound interest in y2. And now what I'm going to do is take a look at the table. And if we look at the table, you can see your values in here, and we just go down this table a little bit. We can see it doesn't take much longer after those 6 years for the compound interest to surpass the simple interest, and so no, it won't always be better. It's just on this shorter time period of 6 years, the simple interest is better. So what we'll do now is take a look at these two word problems. So we have Manny, who's moving out of his house and needs to pack up his belongings, versus Christina, who has her belongings packed and she is also moving stuff out. And so when we're trying to take a look at this, the question is asking us to write an equation to model the number of boxes he has moved over time. The key phrase in this first example is that he moves the same amount of boxes each day. So as we make a table of values here, what we know is that on the third day of packing, he's moved a total of 12, and on the seventh day of packing, he's moved a total of 26. And since it's moving by the same amount every single day, what we know is that this is going to be a linear equation that we are trying to set up. And so as we have this gap of 4 here, we're also going to be taking a look at this and say, well, that's a gap of 14. So we will not be doing next over previous. We'll essentially just be doing slope, which is change in y, so 26 minus 12 over the change in x, 7 minus 3, which would then be 14 divided by 4, which is 3.5. So 3.5 boxes per day is his rate in which that he's moving those. What you'll then do is have to go backwards in your table in order to find out what's going on at term 0 to figure out how many boxes he had started on the initial day. And so we're going to have to subtract 3.5. So then what you'll have here is a 8.5 and a 5 at day 1 and then 1.5 at day 0. I know there's a little bit hard for you to see there, but you're just going to subtract 3.5 each day. That our equation is going to be y equals 3.5x plus 1.5. And then the question is, how many days did it take him to move all 55 boxes? So that's how many have actually been moved. So that's going to go in for your y value. So what we set up is 55 is equal to 3.5x plus 1.5, and that's 55 days, not boxes, so you set it equal to that. Now we're going to subtract 1.5 from both sides to get 53.5 equals 3.5x. You divide by 3.5 on both sides. So that tells us that x is going to equal our 15.28 days. And so we have to actually round that up in order to get a total number of boxes moved. And so really, what you're going to have is a total of 16 days in order to move those boxes. So that's how long it takes Manny. Now, Christina is also moving her boxes, but they're already packed. It says the amount of boxes she has left to move decreased by the same percentage each day. So that's our key phrase here, decrease by the same percent each and every single day. So we're going to still make our table here as we set up our values. And so it says on the 5th day of packing, she had 20 boxes remaining to move. But on the 9th day of packing, she had 12 boxes left to move. So since this is a percentage problem, we know that this is going to be exponential. So for our exponential equations, we know that we have to do some next over previous work. We still have a gap of 4 here from day 5 to day 9, but I'm not going to subtract. What we're going to do is next over previous. B is going to equal the 4th root of 12 divided by 20, which will get you a value of 0.8801, which we would then just round to 0.88 there because the 1 doesn't do us much at the end of that 0. So that's what our multiplier is. So from there you have to divide actually 5 times. So if you go on your graphing calculator and do that, you would take 20 and you would divide by 5 and you would do it again and again and again. On that day 0, what you end up with is a 37.89 boxes, 898, which we would really round up and say that our initial value would be 38 boxes. You could probably, it'd be okay if you left that as 37.89 or 37.9, that'd also be acceptable. So this equation would be y equals 37.9 times 0.88 to the x. Now there's a couple questions here. Additionally, it says how many boxes did she start with? And that's kind of where it would make sense to round up to say that you started with 38 boxes. It also asks us what is the percent decrease each day. And so if we have a multiplier of 0.88, you can turn that into a percent decrease and say that you have a 12% decrease because that's the distance from 1 there. And then the bonus question is how many days until she has moved all of the boxes. And so this would be an example where I would look and type this into my calculator into Y1 and continue to go down that table until I find out where you have a output of a value less than 0.5 so that you would round down to 0. And if you're looking at your table, you're going to have to go down quite a ways. And it looks like that at 34 days, you get a value of, on my calculator, I see 0.49096, which would round down to 0. Remember, in an exponential equation, it's never going to actually equal 0, so we have to find a time when we're going to be able to round down. So that'd be 34 days. So that's a lengthy warm-up, but covers lots of great things that are happening in this chapter 2.